Welcome back to Arts Learning. In this video, we'll be going over path independence. Basically, the concept that no matter what path you have, your energy is going to look similar, which is what I'll explain in more depth now. So, this equation, even though it might look a bit, unfamiliar, it's really just a result of a simple ramp. Where you start over here, right? You have an initial potential energy, mgh, and then at the end you have kinetic energy, 1/2 mv squared. M's cancel out, 2gh square root of that is velocity. So in a frictionless ramp, this is going to be your velocity, okay? You don't need to memorize this formula because it just comes out of the conservation of energy equation that I gave you, right? Initials here and finals here. So we only had potential energy initial here. Here we only had final kinetic energy. So similar, right? Now we're going to explore this in a bit more depth. You saw that velocity doesn't care about like angles or something, right? It only cared about which height you were dropping from. So if there are 5 different ramps, okay? So what if I give you 5 different ramps? One that looks like this, okay, so one that's straight like this. Let me draw the others in different colors. One that dips like this, okay? And then one that dips straight down, like all the way down, and then just keeps going that way, like flat. And then one that does this, as well as one that does this. So all of them end at the same point, right? But they take different paths to get there. So which one do you think would have the fastest velocity at that point? That was a trick question, right? They all start at the same height. So what energy do they have? mgh. They all end at the same point. So what energy do they have? 1/2 mv squared. Very similar, right? Velocity doesn't depend on mass or any other object. It's just the height here. They all start at the same height, which means they have the same potential energy, right? But there is a caveat here, right? Even though they all have the same velocity at this point, velocity is same, which one is the fastest to get there? Which one would be the fastest to get there? Well, we know it's not going to be the straight line because that just, I don't know, it doesn't seem right? It's a bit too straight here. It's going to have a lower acceleration at the start. So it's not going to be able to accelerate as fast. The purple one, it goes all the way down. It has a fast acceleration, but then this curve might slow it down, right? It has to go through this entire curve. This yellow one, it does good, but then it just falls flat. And then it's just rolling like that for a bit. So that might decrease its acceleration. But this path, the red one, that curves just right, just the right amount, right? So it just curves just the right amount. And also keeps the acceleration, is going to be the one that reaches there in the lowest time. It's the fastest one there. Okay? So what I gave you was a more informal definition or informal explanation behind that, right? There are more formal explanations, but I'd rather not delve into that because that goes into calculus and a lot of other stuff that this course doesn't cover, right? So just remember that, however. Now, let's move on to problems regarding these. Okay. So we have a roller coaster train, okay? That starts over here, so let me, okay, it starts over here. And then what does it do? It goes down, all the way down till there's a dip. Okay, so imagine the roller coaster rails are like this. Which car, so this is car 1, this is 2, this is 3, this is 4, this is 5. Which one will have the highest speed at the bottom? Well, you might be like, well, didn't you just tell me all of them are going to have the same speed, regardless of the ramp, right? It's just where they start from. And do all of them start at the same point? Maybe. But think about it. So let me get this here. Imagine that it looked like this, okay? Where the 4th car is in the middle. Here, what do we have here? We have gravitational potential energy from this car, right? The first one is slowing it down because it has gravitational potential energy. So you have bars here, right? You have potential energy and you have kinetic energy. So at the start, you have only potential energy, okay? You have no kinetic energy at the start. But nearing the end of the thing, over here, see what you have. If you wanted to maximize the kinetic energy here, to have the maximum velocity, then here we have a bit of potential energy, right? So that wouldn't really be that optimal. It would look like this, potential energy, but also more kinetic energy. Is there a way we can optimize this? Okay, what if we send it back a bit too much? Okay, not too much. Let's just see. We send it back. What happens? Okay, so yeah, let me draw them. Oh, whoops, not the eraser. Yeah, so now there's 3 cars in the more back area, 1 in the middle, okay, and 1 forward. So now you might be like, okay, well, we don't have much potential energy, right? But what about here? We still have potential energy, right? This is a bit too high. It's still giving potential energy. What's the way we can maximize it to the height is the less, it's the most less, right? So we don't have extra here or extra here. Well, we could do that when the middle car is at the bottom. So let me show you what that's going to look like. First, let me erase all these cars. Okay. Then you can see how if I had 1 here, I had 2 here, right? 3rd one is in the bottom. 4th one is up. 5th one is up. They still have potential energy because both of them have height. But this is the lowest potential energy, right? Both, they have the lowest height here. Before, 1 was too much up, so there was like more height. Or 1 was too low, which means 1 was more up here, which was more height. But here, both of them have the same height, which is also the least. It happens to be the least. So this car over here, which has the lowest potential energy, because it has the lowest height, right? The middle car will be the fastest. Because when it's hit, it hit the bottom. It hits at the bottom at the part where the first and second car, the first and last cars are at their extremes, right? Sorry, extreme minimum here, right? After that, the heights only increase, or they can increase this way or increase this way, right? But over here, both the heights are least, so the gravitational potential energy is least, and the car that has the least height will thereby have the greatest kinetic energy. Okay, so pretty interesting, right? So this was just a misleader, okay? They're all the same. That was just a misleader. Because over here, the middle car is the one. This I just put down to trick you guys, right? Because you might think that because of the ramp, right? That, most cars, they start from the same position. They're going to have the same kinetic energy. But no. It's going to be the middle car at the very bottom, because it hits the ground when what? Both the other cars are at their extremes. Okay, so 3 baseballs are thrown from a cliff with the same initial speed. Okay, so cliff here. I don't know whether someone can stand on this, but we'll see. Thrown from this. Okay, one aimed upwards. Okay, so one goes like this, one horizontal, one aimed downwards. Which ball hits the ground with the greatest speed? In this case, it's all the same, because the previous cases are a bit more confusing, I admit, but it's a bit more intuitive as well, right? And I just explained why that happens. They all start from same height, right? MGH. So they're all going to end up with the same kinetic energy at the end when they both reach the ground. But this one is going to reach there faster, right? Because it's already directed in that path. These can take more parabolic trajectories. But this will reach there faster, but they'll both have the same initial velocity. I mean, velocity final. At that point, when they hit the ground. Okay. So if a 1 kg ball, okay, with weight 10 newtons, is raised 3 meters by 3 different routes. Okay, so 1 kg ball here. So 1 kg ball here. And this is 3 meters by 3 different routes. So straight up a pole. So the flight of stairs is over here, okay? Straight up a pole. So just upward like that. Okay. Up a 5-meter ramp. So it goes upward like that. Up a flight of stairs. Rank the work needed from least to most. Well, it's the same, right? Because each of them have what? If each of them are 5 meters, so no, actually raised 3 meters, right? If each of them are 3 meters, the ramp is 5 meters in length, but 3 meters in height. If each of them are 3 meters, then what does that mean? That means that all of them will have the same gain in work, right? Because it's just mgh. So they'll all have the same gain in work, same energy, which you lose by lifting it that high. Okay, they start at the same point, they have the same gain in work. So all of them are going to be the same. So that was just a bit more conceptual of a video. Next video we'll be going over springs and problems, right? Because I only showed you kinetic, potential, and work non-conservative. We haven't really looked at final or initial springs yet, but we will look at those, okay? So stay tuned for those. And if you want the more complex problems, feel free to check out my video on those at artslearning.com.